No questions at all? If we don't have anything else planned other than to ask you to go to on the agenda webpage, our final announcements are please complete it shows up a little so our final announcement, please complete our post-workshop survey. This is our second online tutorial. We did one 2 years ago, and one of the keys is what to include in these online tutorials, as well as how to make use of in-person tutorials versus online tutorials. We've done in-person tutorials at places like the EarthScope meeting, as well as our now we've sort of switched to doing an in-person workshop within the U.S., alternating years between online tutorials and in-person workshops that have a 2-day tutorial. We found that you really, by spreading out the tutorial over 3 days that is spread out over 5 days, there's a lot more time for people to work and come up with questions. But we're also, it's less sort of interactive in that you're not in the same room able to talk to each other throughout the day, throughout the rest of the workshop. Obviously, it saves a lot on travel costs if everybody's just doing it online. Also, it needs feedback about with respects to what topics to cover. So, we have a lot of examples in the pilot manual, over 30, but many of them are relatively simple. That's to get you started. How do we get you from running those examples to running full research problems that are much more sophisticated and complicated? I'd say that's one of our biggest challenges in having people use a community code. Is it's pretty easy to get people running up simple examples, but they need to sort of gradually build up their expertise, because you can't immediately jump from one of those simple examples to a full 3D research problem, say with multiple faults and complex geometry. It takes a little while to get used to the code, how it runs, knowing how to debug, and sort of knowing how to set up problems. And so that's where we really recommend starting simple, take one of our simple examples, and make it look step by step, go through the steps of changing one thing at a time to make it look more like the research type problem you want. And so looks like there's a question. I'm not sure. It says something about please reply, but I don't know what you're referring to. You're referring back to the how to save and download the recorded flash movies. You can play the streaming versions through the links on the agenda webpage. And next week we'll be cutting up QuickTime versions that can be downloaded. And then when those are ready, we'll post them, and there'll be links from the agenda page, and we'll send out an email to everyone registered on how to download those. Where can you find an exhaustive list of flags and arguments for running .cfg files? So that's where, in terms of all of the pilot parameters, the parameters are really determined by which sort of components you select to run. So as soon as you add in components to the, like saying how many boundary conditions you have and the type of boundary conditions, then we can dump all of those parameters using this pilot info file. But we can't tell you, what are all the sort of components. We can give you a list of all the components that are available, and that's in the appendix of the manual. And then within the various sections of the manual, we sort of describe each of those components in detail. And all those parameters you can set either on the command line or through the .cfg files. And so it's really the parameters really are sort of a runtime specification in terms of which components you select, because you don't necessarily have to have a fault. You could have any of several types of faults. For the Green's functions, we had one type of fault. For prescribed slip, we had another type of fault. For the spontaneous rupture with fault friction, we had a third type of fault. All of them have their various sort of subcomponents with defaults. And so it's really sort of hard to sort of say, for a dynamic rupture problem, here's your list of parameters. Because maybe you have one fault, maybe you have two faults. And so that's where really finding an example that matches closely to your problem will give you an idea of all the different settings and all the parameters that you need to use. And you'll notice things like specifying the mesh file name. You know, we use that in every single simulation. And so, you know, yes, you can get that information when you run the pilot info. And so I would say using the combination of the pilot info and looking at examples and looking through the manual are the best ways to get an idea of sort of what components are available and how to put them together to create a simulation. It looks like we'll get a few more questions, which is good. So any references for using Green's function from pilot for inversions using other codes? No, I don't have a reference. The Green's functions feature has been in pilot about a year. I don't. That's a good question for Charles. Charles has been using the Green's functions capabilities, and so we'll pass that on to Charles and see if he can come up with a better answer. So I'll make note of that here. We'll send it into our question list, and we'll get an email to Charles and get an answer for you on that. But generally, I don't have anything off the top of my head. Aaron had a question. When specifying output files, is it simply a matter of writing filename.vtk versus filename.hdf5 in the .cfg file? The answer is no. We need to change the type of writer and the parameters. So that's a good thing to look at because it shows some other issues as well. So let's look at. So this example here was running using the default is VTK output. And so when we want to use HDF5, we have to change the type of writer. And so it's this line right here is changing my writer from a data writer VTK mesh object to a HDF5. So this is the type of file that I'm going to be writing, HDF5 external mesh. And here I'm telling it that I want a time step of essentially 0.005 seconds. So I'm telling it for the, let's see, this is going to be just over the volume. I'm telling it I'm going to control how often you write output by specifying the time step, and I want you to output time step essentially 0.05 seconds. Now, why did I not write 0.05 and I wrote 0.049999. It's because when we non-dimensionalize units, sometimes 0.05 is going to end up as 0.05000001. And if I say I want output every 0.05 and my time step is 0.1 or 0.025, then round off errors, I may not get it, every 0.05 seconds. I may get it every 0.05, and then all of a sudden once it'll skip one, and because due to round off errors. So I tend to, in my simulations, I tend to specify a time step that's basically epsilon smaller than the time step that I want, within sort of round off errors. So, by doing, I know my time step is something like 0.025, and so by giving a few more digits in my time step minus epsilon, I'm going to get the time step that I want. Now let's look at the pilot parameters file for our data writer, and so that then we can see all the parameters. And so for my, you'll see my data writer. That's partition 1. So let's go down here to. So I got a lot of information. So my data writer sits with. This is in my. There's an output manager object, and so this is my output fault dynamic. So there is a special, whenever I specify that I want a fault that for a dynamic rupture, the fault cohesive DIN object, it creates an output manager for the output on the faults, and that output manager keeps track of the cell info fields as well as whether I want to, how often do I want the output? Do I want it to specify skip so many time steps between output, or do I want to use the time step? And that's the time step I'm using. Then it tells me, in the output manager, I can also specify, what fields I want. And so this I specified in my pilot app.cfg file. I specified that I wanted the initial traction value, the normal direction, strike direction. If I'm outputting the values of the quadrature points, I do the averaging. In this case, you notice my default was null because I don't want the null filter. I don't want any filter. There's a coordinate system, and then there's this performance logger, the vertex logger. Then down here, here's the actual. So I first select sort of my basic output parameters, and then I say, here's how I want you to use this file type for writing output. And so that's what my writer is, and I've set it to my data writer HDF5 that was set in my pilot app file, and then it has a file name for the output. My VTK files have a not just a file name, but they also have, because we write the timestamp in the file name of the output, when we convert years to seconds, we don't want to see seconds as, some value of 10 to the 7th. We want to see things, if we're writing out every 5 years, we want to see T005, T010, T015, T020, and so forth. And so there's a sort of time constant and a value and a format so that we can specify, how many significant digits do we want in that timestamp and the value to normalize the timestamp by. And that's set, those are, you'll see those used extensively in like 3D Hex8 with our VTK output. Other questions? We're now down to our last 10 minutes. So I saw, so if you want to compile in your cluster, what things should I take care of? So let's look at, let me go to the pilot installer. And let's bring up the install file. So the very bare minimum, you need a C compiler, the ability to unarchive tar files, and you need to be able to, you need wget or curl to download files over the network. And so some of the things you need to be aware of are in these big capital letters up here. For one thing, we recommend that you run in the configure script in a different directory because you will probably get something wrong the first time you try and build it. And if you build in a different directory, you can just wipe things clean and not wipe out the installer code and have to re-download it again. And the other major warning is that if you get it wrong and start over, you not only want to remove where you're building things, but also where you're installing things. And so we've seen people who, the installer, they come up with the wrong configure arguments, and then they rerun it again, and maybe they get a little farther, but but by changing the configure arguments, they built something already, and it's starting to use those that software that's been installed, and it conflicts with what they're trying to build, or they've previously tried to install, and stuff is in their path. And so it's very important that you start from as clean a slate as possible without other stuff getting in the way. Particularly other MPI versions if you're having the installer on your build a MPI on your desktop. And so there's a bunch of important information about how to get started, and then here's sort of some important. So let's go down. If you're going to run on a cluster, so here we have sort of some suggested configuration options for run on a cluster for how you build Pilot on the cluster. What you need to have is you need to have your compilers installed, and you need to have MPI installed and configured properly for your cluster. And then basically you can just tell it to, it's best usually to have the installer build the Python for you because the system installed Python may not have been built with the compilers that you're going to be using, and you need the Python to be built with the compilers that you're using and that built MPI for everything to work properly in parallel. And make threads so you can use multiple building threads with the installer. That on a cluster on the front end with 8 cores, you can generally build Pilot in about half an hour. And where to do the installation. And this will go through and it'll check to make sure which compilers you've specified. That's generally what, MPI-CC, MPI-CXX, and MPI-F90, what are available, what does it see in your environment that's in your path. It makes sure you can, do some checking. It tells you basically what's been installed. And so then you run, after you do configure, essentially you need to, it's going to create. So whenever you use the binary, you do the source setup.sh to get your environment variable specified correctly. The Pilot installer configure script will actually create a file for you for the parameters that you specified when you ran this configure, so that it'll tell you, it'll set up all your environment variables for you when you run the source.setup. And then you make, and then essentially, then once you're all done, you can do make install and then run. And so there's some additional troubleshooting stuff at the end. But basically, to run the cluster, you need your compilers, MPI, and basically tell Pilot to install everything else, including Python. Any other questions in our final couple of minutes? Okay, what does the quadrature mean? So let's actually use the whiteboard here. So here is my quadrilateral cell, and I want to integrate one of our finite element integrals over this cell. And so what the quadrature rule is saying I want to do a sum. I want to evaluate the basis functions at the points to do a numerical integration. So you can think about, if you're using a trapezoid rule to do an integration, this is what type of trapezoid rule do you need in 2D or 3D to accurately integrate a function over this quadrilateral cell. And what the quadrature points is telling you is where here in the cell to pick your points. If you pick your points at your vertices, your basis functions at your vertices have very specific values. Generally, they're one at the basis function for this vertex. You can't see my pointer. The basis function for this vertex is going to be 1 there and 0 at the other vertices. And the same and similar with the other vertices. And so I end up actually picking the vertices to be your numerical quadrature points, which might seem natural, is actually not as accurate as sort of picking points, oops, turn off my arrow there. Picking points such as there, 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 and there. So with those, there's with some linear algebra, you can figure out with, given the basis functions that you have and a polynomial of describing a field over my quadrilateral cell, you can come up with the coordinates that will allow you to exactly numerically integrate by evaluating the basis functions at these points. And the weights for each of those basis functions is determined by the number of points that you have. And so, say for example, so when we do, the default is second order quadrature, and so we call that 2 by 2 because in this direction we have 2 points, and in this direction we have 2 points, and they're on a regular grid. Now then we also can have 3 by 3 integration, which then we generally have, that doesn't show up very well at all. Let me get a dark green here. So I generally have a point in the middle. I guess I'll use pluses. Maybe a thicker. There we go. That's nice and thick. And so with third order quadrature, I tend to have, I'll end up with 3 by 3 quadrature, and my quadrature points will look something like that. So that's the quadrature scheme, quadrature order, and what those values are. So this is when we have, this is the fiat is our finite element tabulator, and these are Lagrange cells because that's the family of how you build up from lines to quads to hexes. Then we also have our fiat simplex. These are things like our triangle. That's not a very good triangle, but you get the idea. And so here, generally, we would have, say, we might have a single quadrature point to exactly integrate a linear variation, or we could have sort of a 3-point quadrature. That would be I believe that's second order quadrature for a triangle. Does that answer your question? And if you're wondering like where any introductory finite element texts if you just look up numerical quadrature or Gauss quadrature, it'll explain how you get your quadrature points. And it'll probably give you a table of the various quadrature points for the different cells. That's something pretty straightforward to look up in an introductory finite element text. Any final questions? So if you run an interseismic simulation, do you need to specify the time of your rupture to put in earthquakes? So an interseismic, so it depends on what you're trying to model. So in the interseismic period, you could have transients left over from previous ruptures. And in that case, you do need to put in your slip to generate those transients. If you're just trying to see how the fault is loaded via, say, the strain field, then you'd be moving your boundaries. And so if you're doing seismic cycles, then yes, then you need to, you can do your seismic cycle either if you know when your earthquakes occurred and you want to and you know what slip distribution you want, then you can use a prescribed slip in our kinematic fault interface. And so you would specify, using such as, let's see, was it step 8 in the 3D hex 8, where we had multiple earthquakes being applied. That was essentially sort of an interseismic deformation case. Where we prescribed this, we had creep going on down at depth, prescribing having the boundaries move that loaded the fault, and then we had prescribed the slip to catch up. That was a very, very simple case where there really wasn't any deformation accumulating, so you didn't have viscoelastic relaxation. But you could also then, as we do with our friction examples in steps, I believe that was like step 12, 13, or 14, where we had seismic cycles with the stick-slip behavior. There we drove the deformation of the boundaries, and then the fault failed when the friction criteria where the stresses exceeded the friction criteria, then we got the stick-slip behavior. So if you want to do seismic cycles with quasi-static, you can use either the prescribed slip if you know your slip time, if you know your earthquake history. If you want to example the physics to get a specific history, then you'll use the fault cohesive dynamic object. And in both cases, I would recommend looking at the examples in 3D hex 8 and picking the one that best matches what you want. As you get sort of more complicated rheologies and start looking at viscoelastic relaxation in 3D, those simulations can take a while to run. So that's where the solver stuff starts to become important. Final call for questions. Okay, I don't see any final questions, so I think we're going to wrap it up. And you're welcome, and thanks for participating. And we look forward to feedback through our post-workshop survey and perhaps seeing you in person at a future meeting, whether it's AGU, an ERSCO meeting, or another meeting like that. We hope your pilot is useful for you.